My name's Kevin Holbrook. Today our topic is assessing performance with SOLIDWORKS tools. So I've been a SOLIDWORKS user for over 20 years, and one of the themes that we hear a lot during the year is all about performance. You know, how well your part reacts, how well your assembly reacts, a little bit about hardware. Today we're going to look specifically at some tools in SOLIDWORKS that will help you to assess why you might be having some performance issues. There are many permutations as to how you use these tools and what kind of information you can glean from them. My hope today is to introduce you to them and let you to your graces to be able to utilize them how you see fit. So a couple of housekeeping issues before we get going. If at any point during the presentation you have any questions, if you could just post them in the question section of the GoToWebinar window. At the end of the presentation, I will go back in and answer any outstanding questions just to make sure we've clarified anything. As always, this presentation will be archived and placed on our YouTube channel. So if you happen to have to step out for a period of time, in just a few days, this will be up on the YouTube channel for you to review as well. So let's talk about the agenda here for a moment. I kind of broke this down into 5 different areas. First of all, just performance overview, you know, what it means, where the issues might come from, some tools to recognize the issues, some approaches maybe to make it better, and then at the end I'm going to talk about a new approach that I think is something that would benefit everyone if they could implement this within their design structure, and it won't affect how you design almost at all, but it will absolutely help you with performance later on. So let's go ahead and get started here. So the first question, obviously you can't answer, but you know, how do I know if I'm having a performance issue? There's a lot of things that can contribute here, but you know, how do I know? When someone calls you up or you're thinking there's an issue, what is my response to this particular question? And here's what I say the answer is. It's really two points. Either A, I'm maxing out my hardware resources. I mean, my computer just can't keep up with what I'm telling it to do. Or whatever you're doing is hurting your productivity. Okay? So with that answer to that question, if we look at this image versus this image, which one would you think I would have a performance issue with? I don't know. The real answer is both. And the reason behind that is related to the hardware, the software, the model. Any of those things could either max out the hardware or hurt productivity. Now, it's all relative, right? So that first image, and let me just go back to this for a moment, that's just a weld mitt with multiple members. Now, depending on the equipment I'm running that on, it can certainly feel slow and hurt productivity. Vice versa, the machine on the right, I could have a really souped up machine and not have any productivity issues at all. So I guess what I'm getting at with this particular slide is there's no way to just look at an assembly and say, this one's going to hurt me. You know, this one's capable of being run on a, you know, a Pentium 3 with 2 gigs of RAM versus, you know, so there's no way to do that with just a visual. Okay? So back to this slide, you know, is it the hardware, is it the software, is it the model? They all play a role in potential issues for performance. On the hardware side, I think we've got a pretty good grasp at this point as to how each piece of hardware affects your experience in SOLIDWORKS. If you want to know more about that, feel free to email me at kevin@CADimensions.com. I can send you a presentation on our hardware review. It just gives you some ideas on how we look and where we look for getting the best hardware for the software. Now, when it comes to performance issues of the software, that's certainly possible, right? If for some reason assembly mating is broken in a certain service pack or has an issue or a bug that you're going to run into, that certainly could affect your performance, and I'm not going to discount that whatsoever. But I want to look and focus on the last one. Is it in your model? Focusing on what you can control is probably the biggest part of this. Is let's get your model performing adequately. Let's look at how to analyze how it's performing and maybe do things just a little bit different, a little bit better, so that we know that we've got the best possible scenario when it comes to geometry. It's not to say that we can't look at the software and find issues or maybe get new hardware to progress and be better that way. All three of these work together, but the one that you can control the most and the one we're going to focus on today with the SOLIDWORKS tools is your model, and is the model maybe contributing into the performance. So let's talk about recognizing issues. Now, if you've been around our Lunch and Learn scene for a while, you've probably seen this assembly. I've used this for a lot of other presentations. We want to focus on the tools and how we can utilize them. More specifically, I just have three outlined here. Now, these three tools have several things within them that are going to give us some information about what's really going on. The first one is at the assembly level, comes something called assembly visualization. I'm going to take you through that in depth. For both or all three parts, assemblies, and drawings, there's a tool called performance evaluation. And then the last thing is just the ability to see the file version. I'm going to show you where you can find that information as well. So let's bounce to SOLIDWORKS for a moment. I'll kind of walk you through some of the things that I typically do when I'm starting to look at performance issues. So first thing, I have a file that I need to get open here, and very simple. It's just this grinder. And we know that there's tools built into SOLIDWORKS to open it simplified. We're not going to focus on that in this presentation. I want this thing loaded up. I want to see what's really going on. Now, the first thing when I open, if you look at the status bar at the bottom of the window, I will sometimes kind of watch this if I'm having a problem with an assembly. I'll look for pauses in the open time. You can see right there on that 4001 part. That's quite a heavy pause. Something's going on there. I'll use that as just kind of an indicator. Make note of some of the files that are maybe taking a little bit of time to open, just so that I can remember for myself to go back and take a look if there is a potential issue with that particular file. Now, the first thing in my eyes that I noticed that was fairly obvious was now the save icon has a little message for me that this particular file is an older version file, meaning the file will be converted when it's saved. It was probably built in 2016 or 15 or older versions, and currently has not been converted to the latest version of SOLIDWORKS as well. So that's another thing that we're going to just keep in mind as we go through this. The other thing with this particular assembly, you'll notice in the tree there that I do have an error in the tree. So that, when I'm thinking about hurt productivity, those are two things that I'm absolutely going to make note of. We'll talk about why they affect your productivity here in just a moment. So let's start off talking about the tool called performance evaluation. Now again, it's the same tool for parts, assemblies, and drawings. You can find it on the Evaluate tab. Performance evaluation just provides us a little bit of feedback as to what's going on in this particular assembly. So first part of this dialog says, you know what, there were six dialog boxes that popped up that were dismissed. I have it set up to ignore certain messages, right? So even though I've got an error in the tree, there's some messages that this thing is trying to tell me about. If I select show this part, it actually shows me the file and the message that I'm getting here. In this case, it's a missing toolbox part. But the performance evaluation is going to let me see that that has occurred. Okay. Now back to performance evaluation, you'll notice the second section says all but one of these parts has not been updated to the latest version of the software. So I'm in 2017 now. One of them had already been converted to a 2017 file, but everything else has not. Now notice the little comment here at the bottom, until they are converted, this will affect file open performance. So this absolutely has affected me in some way. Now, if you're working over a network and the speed in which something opens is slow, this is one of the first things you're going to want to tackle is get it upgraded to the latest release. But the performance evaluation tool is going to tell you what parts it's necessary to do that for. Working my way down just a little further, there's a section titled Mate. Now this tells me approximately how many mates are being evaluated or solved when I open this assembly. And the bigger that number, the longer potentially it could take to open, because it has to solve and rebuild the positions of all those components on open. Now what really goes into this number? It has to do with the number of top-level mates. Okay, I'm just going to close this. Remember this number, 57. If I look at the mate group here, you can see that there's a bunch of mates here. Assuming at this point that that's where the 57 is coming from. But here's a little tidbit that will affect the number of top-level mates, and I've seen this in a lot of situations. You'll notice the different icon on this Parker hydraulic cylinder here. You'll notice this is actually set to flexible. Now let me explain to you what flexible subassemblies do. What the software does when you make a subassembly flexible is it takes all the mates from that subassembly and essentially promotes them to the top level mate group, and they all get solved together. Now any of the other subassemblies, all their mates are just, they're not being solved, they're just treated as one unit locked in place. So let's just switch this for a moment. I'll change this to a rigid subassembly. And let's just go to performance evaluation. And if I go down, you can see I've actually decreased the number of mates that are being evaluated. So there is some effect with the flexible subassemblies on the overall open times of the software. Now, if I go down a little further, the next section I want to highlight is the component counts. Because let's say in this case, this is 884 components, right? You may have an 884 component assembly that feels completely different than my 884 component assembly. Now there's many reasons for that, but one of them has to do with how many unique components are in that assembly. If your particular assembly is completely custom with very little duplicate files, you may have 800 unique components. That's that many more components it has to load and rebuild. When you have duplicate data, it only has to load and solve at one time. It may have to solve the position. So potentially the less unique part is going to be a little bit faster. Okay, that's one piece that we often look at. in this section here, and we're going to talk more about that in just a moment. So all in all, this isn't really providing me a lot of information. I would say the previous version, we know this is affecting performance. The mates, we know that potentially can affect performance. And then just the total number of components, which in reality, you're not going to change and make it better or different anyway. So this is just something to be aware when comparing the two. Now, the next thing that I would do in an assembly like this is I would almost always make sure that the software is opening up the files from the correct location. Now, for those of you who don't have this issue, when SOLIDWORKS is opening a file, it potentially uses 14 different paths to find the data. Now, if this is the first time you're hearing that, that could be a little bit scary, because if you have duplicate data anywhere on your server or on your local hard drive, SOLIDWORKS could potentially find it. Now, if I go to the File menu and go to Find References, all I'm really trying to do here is make sure that all of the file references are in the folders I would expect. Now, in cases where I've went on site to look at particular assemblies, in a lot of cases I'm pulling up this Find References, and the references are pointing to a local folder or to a toolbox that no longer exists, or all these different locations that maybe the user didn't expect to be part of this process. So go right down the list and kind of just take a look. Now, how does this affect performance? Well, first of all, if it's finding data that it shouldn't, that means it's taking longer to search and find the file, which could affect your open time. If you're searching on different drives, different letters, if they're not accessible, you're going to get errors. You'll get messages like file not found, like I have in here for this particular assembly. All of those are going to play a role in the performance of a file. Okay? So those are a few things that I kind of get started with when evaluating performance on a part or assembly. But let's put some real concrete numbers to what's going on here. It's not enough just to say, oh, this felt like it opened slower. It's just, it's hard to quantify that visually unless you have two pieces of equipment side by side. So the tool that I choose to use in SOLIDWORKS is a tool called Assembly Visualization. When it's launched, it will create another tab next to your Display Manager. And the intention of this tool is really to report on different things within each of the files that are open in the assembly. When I say report on different things, I'm like mass, volume, custom properties, things like that, that I can just kind of in one list get an idea of everything that's going on. Now there's a couple ways to kind of look and evaluate some of this. Now you can see by default it's going to come up with mass, and I can just sort with the header using the button at the top. The software is going to create these little value bars that show you what's contributing mostly to the value you're reporting. I can also group things as sub-assemblies, just like they would be in the tree, or I can group them as items, like multiple parts in the same grouping. You can see these are the same part number. If I turn on the grouping, it now changes the icon, which we now have in SOLIDWORKS 2017, the ability to group like this. So as of out of the box with Assembly Visualization, I don't really have anything that tells me how my assembly is performing unless I start to modify the columns that are being reported. Now there are several columns in here, 7 or 8, that could potentially tell you information about performance, but let's start at the very top. If I click the arrow to the right, this gives us some of the basic column reporting that we would want. But if I go down to the section titled More, in this we can get access to anything that is a custom property within any of the files that are open, as well as SOLIDWORKS special properties. Now, if I scroll down just a little ways, you'll notice two of them that are going to be very important to my experience reporting performance. So let's just start with open time. Okay? If I select open time, you can see with the sorting that I have one particular file, this file here. Do you remember the number? The 4001. It takes a 9-second open time. Okay? So it kind of validates my hunch when we were opening up that it kind of took a second there. And there's a few right below that, the drum, which is in the center of this thing, that's also taking a little bit of time. Now, you don't have to just report on one quantity. If I right-click up here, I can add a column, and let's just continue to report on things that can help me. One of the others, if I scroll down here, is rebuild time, because open time only affects the initial open. But as I'm working, I may potentially require a rebuild. So let's take a look at the parts that are taking significant amount of time to rebuild. And you can see, once again, it's a common theme. It's this 40448 part number in the drum that's affecting my rebuild time. Okay, or that's the highest number on my rebuild time. So let's keep going with this. We'll add another column. And I want to add another option in here. If I go to a special property under the G section, it's called graphics triangles. Now I'm going to go much more in depth on this, but and explain further. So let me sort by graphics triangles, and you can see that once again the drum is at the top. Now, what a graphics triangle is, when the software hits the video card and says, I need you to render this, I need this to look like a CAD model. Well, the graphics card is rendering this using triangles. It's what they call tessellating, or breaking it down into these triangular pieces, which it then gives you this nice high quality image in the graphics area. Now, how that plays a role in performance really has everything to do with your video card, and I'm going to explain that a little bit later as well. But I can report on this in here. Now, I have a couple other columns that I would report on, and let's say I've done this before. One of the things I like to do is use styles. Now, once I have all the columns set up, all I have to do is save a style, give it a name. It actually saves as an Excel file. You put it in a location, and then you just call it up when you need it. So I want to call mine up, one that I've already set up for evaluating performance. So I'll load a style, call this my performance Excel file. And when I load it in, it brings all the columns that I use to evaluate performance. Now I'm going to drag this right across the screen so I can take a look at all these quantities together. So we already mentioned the open and rebuild times and the graphics triangles, but I can also report on which files have been converted to the current version, which we talked about with a performance valuation, and we talked about flexible subassemblies, so the solving of those upper level mates, and it will tell me if any of the subassemblies at any level are set to flexible. So I have a nice, quick, easy view of evaluating different things. Now there's a couple more in here that could potentially help me, and I'll kind of go through this a little bit here. They're a little hard to dig in when you got this many properties. That's why I would save those out. There's two in here. One is one tells you the number of bodies in each part, either solid bodies or surface bodies. So those are two that I use quite often that help me out as well. And then the last one is this face count. So face count is the number of faces or surfaces on a model. the more surfaces or faces you have, it could potentially affect the amount of solve time or open time. So assembly visualization is important for me to recognize that I have issues. I can see numbers and time and versions and all of this stuff reported to me. Now, I want to just bust out one of those topics before I get into how do we take that and start making it better, okay? The graphics triangles, here's a good illustration of what graphics triangles do. How a software uses triangles to represent an object really affects how we work with our video card. So we always, especially here at CADimensions, we always look at the video card, if it's supported, what level video card, and then the complexity of the model that you're trying to do. Now, usually when I ask this question, how many of you have ever rotated a model and had it slowly rotate, where like almost chunky, and usually get a 50% response rate or more of people that have seen that phenomena? Well, the reason for that is the graphics triangles, the number of triangles that the model has exceeded what the card can handle per second. So that rotation is being calculated dynamically in time, and the video card can't keep up with it. So just looking at some of the current cards that are out there, just to give you some numbers. Okay, the NVIDIA Quadro 4000 desktop card will handle 890 million triangles per second. The Quadro 6000 gets into 1.3 billion. So that's a lot of triangles. But you can see the note at the bottom of the slide here. It talks a little bit about gaming cards, because we're very big on making sure you have a professional card versus a gaming card, because gaming cards, when somebody builds a game, they do it for speed. So they represent an object in a game with as few triangles as they can. Well, gaming cards are built to solve very low triangle counts. It might only get a couple million. Okay. Now back to our SOLIDWORKS for a second there. You know, if we look at the triangle counts of some of these, you can see they're up there, you know, almost 10,000 triangles for one single file. If you've got 800 files and you multiply that out, it adds up fast. The only time this column becomes a performance issue is when you've exceeded the number and you see that slowdown within your card. And I'm going to talk about how we work with that here in just a moment. Okay? So how do I make my files perform better? So it really is a systematic approach to taking what I've just done, open times, rebuild times, graphics triangles, and start with the biggest offenders and simplify and change what you've done to make it better. So let's just take in this case. Let's start with our SOLIDWORKS open and rebuild times. We've got an open time of 1.75 seconds and a rebuild time of 1.61 seconds. So if I open this drum that's at the top of this right here, and notice the triangle count, there's a couple things that I can look at doing here. There's clearly some heavy patterning in this one. I noticed that the file is not converted, so maybe I save the file in the latest version of the software. But the first thing I'm going to look at is what within this model is really taking the most time to calculate. Now this is where performance evaluation comes into play at the part level. Because now that I know that this model is heavy on the assembly, I'm going to go to the performance evaluation on the part, and I can see clearly that the two patterns that I have here are affecting the time the most. Okay. With that said, I might start right at the very first one and edit the pattern just to take a look at what it has going on. And notice I can edit right out of performance evaluation. Now this particular pattern is a cut that's being patterned, and it's not using anything end condition wise that's crazy. It's using an axis. There's nothing really here. But one of the tools within the pattern dialog that I just think it's good to keep in the back of your mind is this geometry pattern. What this does is instead of solving the cut for each pattern instance, it just tries to copy the geometry from the first cut to the rest. Now in this particular case, because these fins are at an angle, it's really not the same geometry as it goes down the line. The faces get cut differently because of the angle. So you'll see here, if I try to turn this on, this thing's just going to holler at me and it ain't going to work. Okay. So this particular pattern, there's nothing that I was able to help with. But notice my time immediately went down still on that pattern. And this is simply because I've converted it to the latest version of the software, and it just rebuilt that feature and gave me new times. Now I do have another pattern here, a circular pattern, that let's take a look at what we might be able to do here. Now, so we're taking an initial fin and we're driving it around the drum here. The reality in this one is every subsequent fin is exactly the same. So here's an instance where geometry pattern would work just fine. When I turn on geometry pattern, the result of the file is the same. But look at this. I've now taken that circular pattern time to 0.14 seconds. Okay. Now, let's just jump back to the assembly for a moment, and let's just take a look at overall where that places that drum in the grand scheme of things. So my drum is now third on the list with a 1.75 open time, not nearly what it was, smaller rebuild time, still a high number of graphics triangles for this particular object. Let's take a look at what the upper item happens to be. This is nothing more than a set of blades or to move something through our machine. And if we look at this one, performance evaluation, this is the one that took so long to solve, so long to open. You can see almost 9 seconds to do the cleat pattern. This cleat feature, which is the center, and then patterning it. Now, I can certainly try in this case to edit the feature and maybe do a geometry pattern. Let's just see how that's going to affect things. You can see it points me to some other options here, but you can see that it doesn't work in this case. Okay, so there's some issues. I can't really gain anything from this particular part with this type of pattern. So how do I look to gain some performance at the assembly level for this particular model? Well, it really comes down to simplifying the model a bit. So what I might do in this case is create a simplified version of the cleat. Maybe keep the initial dimple or cleat on there so that it's there, but remove some of the other detail, the pattern in this case, because at the upper level assembly, I don't need all of that. Now, if I look at the performance evaluation of this model now and look at the rebuild times, considerable difference. So the rebuild in this particular case, in this model, was being affected almost highly by that pattern. So at the assembly level, we're going to want to do the same thing, right? So we essentially swap that out, and you'll notice my drum is back to being the top of the list. the drum is at the top of the list for open and rebuild times, and that has to do with the patterns. But how else can I make this a little bit simpler at the upper level? And this is just another example of simplification. I can come in here and highly simplify the drum without all that detail to it. And you'll see that, again, I'm affecting my overall rebuilds. Let's just swap out the configuration here. And you'll see that the numbers for this drum drop it way down within the list. So what I'm hoping you get out of this today is not an exact answer on how to make it better, but the tools to be able to evaluate, to go in and look at the possibilities of what might be slow, what might be affecting performance, because let's face it, every time we have a so-called performance issue, we're not going to be able to go to IT and get more resources or get a better computer, or we're not going to have the concrete evidence to say SOLIDWORKS is doing something. In some cases, there's things that you can do that can make things better. And I hope that this gives you a little bit of guidance on how to do that. So let's just close with what I would call a new approach for starting the process of creating better assemblies. In most cases, there's some simple ones that are easy, right? Every time you go to a new release, when you get a file open, you save it in the current version. Make sure all the files you have open are saved in the current version. The subsequent loads are going to be faster. You want to look at things like your end conditions, using geometry pattern, using up to surface, up to next. Those take longer to solve, therefore will change the way that we model a little bit. Using flexible subassemblies, knowing now that they affect your assembly. Hopefully you only turn them on, calculate the mates that you want at the moment, and then turn it off. Don't leave them on, okay? But let's talk about this approach really as it relates to simplification. I'm going to get some files closed off here. I want to provide you some real concrete proof to the differences that the simplification process makes, and then give you a method to go about this. So I would just want to open up an assembly here. Let me just get that from my desktop. And this assembly is very small, but it's better. It'll better illustrate what's going on here. What I want to do for an assembly is create a version of that assembly that I can use downstream that is highly simplified, that will make all levels of an assembly easy to work with. Now, that just means that when I'm modeling, I'm going to create a version of each part that is simplified so that in the end, I get to an assembly, an upper level assembly. Now I'm going to place this in something else, and I have everything simplified. It still looks like the same model. I'm missing some fillets, I'm missing some extruded text, I'm missing a few different things, but for me to put this into a large piece of equipment, I'm not going to notice any of that geometry at that upper level. So creating this simplification just makes it that much easier. So there's two ways to do this. One is on an existing model. All you're going to do is open up the model. You're going to create a configuration called simplified, and then you're going to go through the feature tree and suppress the features that are not necessary. Now you're going to want to do this before you start placing this and positioning this in the upper level assembly. Therefore, you're not removing anything that may affect. So that's on an existing assembly, and I'll say this, I don't think any of us have time in our organizations to be able to say, oh, my assembly's slow, let's go back and simplify the whole thing. I just don't think that's happening. I think we live with the performance that we're dealt with at that upper level, and we get through it. So my simplified approach here at the end is really about what I can do now to make sure when I get to the end that it is simplified. And here's my recommendation. go back to your existing templates. So go File New or File Open on your templates. Open up the part template that you use. Go right to the Configuration Manager and add a configuration to the template called Simplified. Okay? So as you're modeling parts, the last thing you do before you do a Control-Q save is you jump to the simplified configuration and remove a little bit of detail. It will already be there for you, the configuration. So it's literally right-clicking on a few features and getting rid of it. Now, when you start to get up to the next level assembly, now that you've created all the simplified, what you don't have to do is come here and say, you know what, add a configuration, simplified, and then you go to each part and make sure it's loaded the simplified version. Because again, that adds a lot of work to the process. So let me show you how this can be done automatically with SOLIDWORKS. Let's say I knew I was going to use that model in the upper level assembly, but I wanted all the simplified parts with it. When I do a file open and I find the assembly, under the under the configuration option is an option called Advanced. Now, you may have never selected this or even know what this thing does, but once you say Open, it brings up another dialog that says it has different ways of opening the models. You know, I can create new configurations, I can show only the assembly structure, but the one I'm looking at is this one here. So use specified configuration for part references when available. You type in the name of the configuration. So now if you've followed the processes I've talked about and every part gets a simplified version, when I say OK to this, when it's opening up the model, it's looking, hey, is there a simplified version, simplified, and it will open up the assembly completely simplified for you without you having to create configurations all the way through. Now let's just talk for a moment about what that's going to gain you. I just have some examples here, and these are just Excel files just showing the results of this particular assembly, just on some of the things that we've talked about today. Open time, rebuild time, and graphics triangle. So this right here is the simplified version. Let's jump to the other one. I think that will be the best place to start. So the full version took 2.4 seconds to open, 8 seconds to rebuild, and used 116,000 triangles. Okay. The simplified version, considerably less. 1/3 of that time to open, half the time to rebuild, and half the graphics triangles. Now, if this thing is in the assembly 8, 10, 12 times, you can see we've really helped ourselves with performance because of these numbers. So this process does work. I think it's a method that you can implement very quickly and easily. Obviously, you have to have everybody in your organization on board to do that. And over time, everything will just have a simplified version to it. So I hope with today's session, you got a good idea as to how you can look at different results, maybe put a keen eye as to why, and maybe I didn't give you enough to know exactly how to tackle them because there are so many permutations, but if you can at least identify what potentially could be the issue, you can contact us on tech support or even attempt to edit those features and edit those parts to see that maybe there's some change that you can make. So I want to thank you for attending today's session. I hope you enjoyed. We'll go ahead and answer some questions.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.